Hello people, thanks for clicking over this video, and if you wanted to learn PSpice, then this is the right series that you have clicked on. Now in this video we're going to discuss about buck converter and we will simulate it on PSpice. So there are three topics that we're going to cover. The first topic will be basics of buck converter and its modeling. Second topic will be derivation of voltage across inductor. So we'll derive the voltage across inductor in terms of its D off and D on, plus what is the amount of current which is flowing through it. Apart from that, we're going to discuss design and simulation of a buck converter on PSpice. So these are the three topics that we're going to cover in this tutorial. Now I have a very important information for the people who are planning to get OrCAD license. There are special OrCAD offers going on EMA EDA website. So I'll put link in the description for our Indian, US and UK community. You can go to that link and check out the offers. But if you are planning to purchase OrCAD Standard Suite or OrCAD Professional Suite, you'll get up to 50% discount on each of these. So please go to the link, check out their codes. With that said, let's roll the intro. We'll start with basic of buck converter. So we have already seen a basic circuit of buck converter which will consist of a battery which will be V in our case. Then further we'll connect switch to a battery. In our case we're going to use a MOSFET in place of switch. Then further we'll connect diode, let's name it D1. After that we'll connect inductor, capacitor and load resistor. So this is the basic circuit of a buck converter. Further on this, we have few feedback on our buck converter. Using that, we can able to control or modulate the width and frequency of the switching. How we can do that? So there will be current feedback and voltage feedback which will directly go to control logic. Further, it will be connected to a modulator where we will modulate our output waveform or pulses in terms of their width or frequency, and it will be directly connected to MOSFET. So this is how we control the load current and load voltage of a buck converter. On this circuit, the problem statement is switching part. So we have to tune these three elements which has MOSFET, diode and inductor. Now we have to tune those, we have to do few analysis which will be time domain analysis or transient analysis. After that we'll go for the steady state point analysis which will be our DC sweep and then AC sweep. So we're going to perform these analysis on an equivalent circuit on PSpice. Now the fun fact about switching assembly is we can create different CCM converters using it. So switching assembly consists three important component which is inductor, switch or MOSFET and diode, and we can also represent it either way. Now we can create buck converter using the first combination of switching assembly. Similarly, we can create boost converter or buck boost converter. Now let's talk about continuous and discontinuous switching. As I have told you, the switching part unit consists of diode, inductor and switch. We can also represent it like this A node, B node and C node, where T on, that means when our switch is on, the current will flow from A to B node, and when switch is off, the current will flow from A to C node. But there is one more node between B and C that will be our discontinuous switching. So there we will not get continuous waveform of switching or charging or discharging of inductor. Alright. So we're going to discuss that using a waveform. So here T on represent the switch conduction time, T off represent diode conduction time, and T DCM is discontinuous switching. Let's go into a little bit deeper in the concept of CCM. So as I've told you, this is the model of a continuous conduction mode where we're not going to cover discontinuous switching as of now. Now imagine what will be the amount of current which will be flowing through inductor and what will be the waveform of that. So the amount of current which will be flowing through inductor will be IA average, which will be equal to the inductor current. This is our first expression. Now how this charging and discharging of an inductor looks like. So it will be something like this, right? So this will be charging and discharging of inductor, right? And what will be the amount of current flowing through inductor? That will be the average of this switching waveform. All right. So this will be IA average or IL. Now let's talk about when switch is on. When switch is on, only this part of inductor will work, right? This is for off. Now this is again for on. If we'll divide them quickly. All right. So when switch is on, we'll see only this waveform, right? Okay. Now what will be the average current flowing through node A to node B when switch is on? So that will be IB. So IB will be the average of these waveforms. All right. Now let's talk about when switch is off. When switch is off, only this part of the waveform we can able to see on our scope, right? If we are talking about only off state. Okay. What will the average current flowing through node C? That will be IC average, right? Now we're going to calculate this in term of the duty cycle. So let's see what we'll get. Firstly, let's talk about on state. So when we'll use first expression that we have already calculated. The amount of current flowing through inductor will be IL or average current. This will be our first expression. The waveform will be for T on. It will be something like this, right? And this will not see on our scope. All right. So this will be time to charge the inductor, right? And this is the total time period. We'll represent it with TS. Now we'll talk about another expression, which will be the average current during T on. That will be the inductor current multiplied with duty cycle of on state. If we'll further use the formula of D on, it will be inductor current multiplied with time on divided by total time period. All right. Now let's talk about off state. So during off state, we'll not see anything when inductor is charging, but we'll see the waveform of discharge, right? So that will be T off, and this will be the average current of that, right? So the expression for T off or the current flow during off state, that will be inductor current multiplied by D off. And if we'll further divide it, it will be inductor current multiplied by T off divided by total time period. All right. So using these three expressions, when we'll apply KCL on any of the circuit using switching element, we can able to calculate and derive the waveform. We'll discuss that in detail during the buck converter derivation. Further discuss continuous current source model. So on this, our first current source will be IA, and we can represent it with GA, and it is further divided into on and off state, which will be GB and GC. Okay. Now, where GA will be is equal to the average current of A node, which will be equal to inductor current. GB will be equal to inductor current or average inductor current multiplied by D on, and GC will be average inductor current multiplied by D off. Now further derive the inductor current, then we will get DIL divided by DT is equal to VL upon L. Let's quickly implement continuous current model on buck converter. So let's draw the buck converter circuits first. Now let's replace switch, diode and inductor with GA, GB and GC. Now we know what is the expression for these current sources. So GA will be is equal to the inductor current or average inductor current. GB will be is equal to average inductor current multiplied by D on. GC will be average inductor current multiplied by D off. Now let's apply KVL on the switching unit. So this is the switching unit where we have node A, B and C. And from there we got to know VL will be is equal to VAB multiplied by D on plus VAC multiplied by D off, where VAB is equal to V out minus V in and VAC is equal to 0 minus V out. Let's move to simulation part. But before starting the simulation, I wanted to brief you about the schematic. So here we are using a 50 volt DC input supply, which is further connected to a MOSFET, which is IRF 150. And this MOSFET is switching using a pulse generator. On pulse generator, starting voltage is 0, V2 is 20. There is no time delay. Rise time and fall time, we are going to use 1 nanosecond. And the width of or the on time of that width or pulse will be 20 microsecond. Time period of the pulse is 50 microseconds. Further, we have connected inductor. We'll discuss how we got this value, capacitor, load resistor and the diode. So this is a simple open loop buck converter circuit where we are giving 50 volt and getting 20 volt output. If you recall from our initial discussion, we have also created a block diagram of closed loop buck converter where we are taking feedback from voltage output and output current that was going to control logic, and from control logic we were modulating the on and off cycle. So this is open loop circuit. Now we're going to discuss the calculation part. Let's start the calculation part of buck converter. So we'll start from D on. So D on will be on time divided by the total time of T on plus T off, or you can see the duty cycle, right? So which will be 50. We'll get 0.4 from that. Let's do the calculation for V out. So V out will be V in multiplied by D on, right? So from there we'll get 20 volt, all right? So this is how we have defined what should be the input voltage, what is the relation between input and output voltage. Let's calculate the L minimum or the inductor minimum, which will be 1 minus D multiplied by R or load divided by 2 into switching frequency. So in our case, it will be 300 microhenry, right? If we'll go back to circuit, and you can calculate what will be the switching frequency of that, right? So from that we got to know it will be around 20k. Now this is the minimum inductance. So what is the inductance value that we have to use for that? So there we use a multiplier which will be 1.25 multiplied by L min. So this will be 375 microhenry. Now the next step is we have to calculate the capacitor, or the one we are using to remove ripple. It will be 1 minus D divided by 8 into inductor into ripple factor. So ripple factor is nothing, just a delta V upon V out, which is the RMS of AC component divided by average or DC component, plus multiplied by switching frequency and its square. Alright, so this calculation, if you'll do that, if you put all these values, I'm considering ripple factor 0.4 and you'll get 125 microfarad, right? So this is how we got all these three values. What should be the output voltage, what should be the capacitor, and what should be the inductor value. Let's simulate this circuit. So here I'm not going to tell you how I placed all these components, because that we have already discussed on earlier levels. Now here we're going to probe couple of things. So we're going to probe V out, but before that let's do the simulation setting. So as you can see, I'm going to run it for 5 milliseconds and this will be the maximum step size. All right. Press OK. One will be V out, and before that, let's delete this one. I'm just going to place current probe on output. Sorry, it should be on the pins of the component. And what is the input current? So this is first thing I just wanted to simulate first. Let's do that. All right. Now we're going to add another plot. There we wanted to discuss, or we wanted to see the waveform of output voltage. So let's put output voltage there. Plus let's another plot there. And here I wanted to see the differential voltage between the inductor terminals. So let's put differential probe between inductor. So these are all the things I wanted to discuss here. So we'll discuss that in very detail in the next video, like why this current is going like this, right? And why we are getting this waveform which is going downward and then it is kind of stable here. So we're going to discuss these waveforms, their slopes in very detail in next video.